Okay, so yesterday we went over problem solving, in other words, applications. Today we're going to go over first how to solve inequalities, just like in the abstract form, and then we're going to go over inequality applications. So, and just a reminder, tomorrow is going to be our review class. During our review class, I typically go over just a bunch of examples from this chapter, and then I usually send you guys home with like a review, like a practice test almost. I don't require that you guys turn in the practice test, but that's just what to expect from me for study for the next exam. Okay, so let's talk about solutions of inequalities versus solutions of equations. So we already learned quite a bit about solutions to equations. We learned about the additive and multiplication principles and sort of how to solve for x with those. So today we're going to be talking about how to do the same when you have inequalities. So let's just keep in mind, when we talk about equations, an equation has a single solution or a finite number of solutions, right? Usually an equation has a solution like x equals 5. An inequality will be an interval, so a lot of different solutions. So for an inequality, an answer would be any x greater than 5 will solve this problem. You know, that's kind of like what we're dealing with. The only difference between solving inequalities and equalities in the end, the only functional difference is if we multiply or divide by a negative number, we flip the inequality, right? That's the only difference in the end. If you know how to solve equations, then you can solve inequalities as well. You just have to remember to flip the inequality if you multiply or divide by a negative number. So let's take a look at what this looks like in practice. So first of all, if you haven't seen this yet, an inequality is a number sentence using one of these 4 symbols. A solution is any number that makes the inequality true, right? Just like a solution for a regular equation is anything that makes that statement true. A solution set is all the numbers that make the inequality true. So on these next examples, let's just go through and determine whether or not these are solutions to this given inequality. Y greater than or equal to 6. What about this first one? Is this greater than or equal to 6? Yeah, so yeah, that's a solution to this. What about this one? Negative 4. No, negative 4 is smaller than 6, so this is a big no. Right, so this is one of the solutions to this inequality. One of the things we're going to be doing fairly regularly when we talk about inequalities is graphing them on number lines, right? This is very similar to just graphing numbers on number lines. We just specify an interval rather than a point. So, real quick, is anybody not sure quite, is everybody familiar, I should say, with this notation? Do we all know that this is 3 is less than 4? Has anybody not seen this before, just so I know how much detail to go in? Okay, everybody's seen this, then I can assume that you guys know what I'm talking about here. Okay, so when we talk about graphing intervals or graphing inequalities, the things that we need to pay special attention to are the difference between this symbol, right, greater than, and then this symbol, greater than or equal to. The endpoints of the interval that you specify on this graph will change according to what this is. So let's do this first one. So x less than 2. What I do when I want to graph something on a number line, I label 0 always, and then I label the point in question 2. If you really want to, you can put a 1 in the middle here if you want. And so I'm just going to specify all points that make this statement true. X less than 2, not equal to 2. So the point 1, that makes this a true statement. The point 1.5, that makes this a true statement. 0 is a true statement. In fact, anything on this side of the number 2 is going to make this inequality a true statement. The only thing we have left is to determine the behavior at 2. So when we have a less than but not equal sign, there's 2 ways that we represent this. In the book, they typically tell you to represent it with a round bracket right here on the number line at the point 2. And that's a great way to represent it. I'm really unused to using that, and so a lot of times in class I don't use that just because I'm very much used to using this other version, which is the same, except for it's an open dot instead of a round bracket. That means it comes all the way up to 2, but doesn't quite reach 2. And to me, an open dot makes a lot of sense for that, whereas a closed dot means it can reach 2. So let's go over that other type. So for this one, y is greater than or equal to -3. Okay, so I'm going to mark 0. I'm going to mark -3. Now I have y is greater than or equal to -3, so this demands a different kind of bracket or dot. In the book, they typically use a square bracket for the end of this, and that means it's greater than or equal to that point. And then you draw a line over to positive infinity, because these are all the points that make that statement true. What you'll be seeing me doing more often probably, like kind of my version of this, is a closed dot at the point 3. And then it goes to infinity. All right, so closed dot or square brackets, that indicates equal to, right? Greater than, less than, or equal to. And then an open dot or a rounded bracket, that indicates greater than or less than, but not equal to. Okay, for this particular guy, notice this interval is just sandwiched in between 2 points. So like always, I label 0. -2 is right about here. +3 is over here on the positive side. So this says that any x that is greater than -2, but also less than or equal to a +3 would work. So all I do is I write out my proper interval end over here, which is an open circle at 2, or a round bracket if you prefer, and then that extends out to the +3, the other end of the interval. And there I put a closed dot, because that one is less than or equal to. Right? Alternatively, you could use a round bracket here and a square bracket here. Okay. Okay, so for these examples, we're just going to be going through and graphing each inequality like we just did. Are these, whoops, I have an extra page. Never mind. Okay, so we went over graphing inequalities. Let's talk about the 2 notations that we use for the solutions, right? So there's 3 forms that your solutions will come in for inequalities. One is graphing. We just went over that, so that's one solution form. The next one, this is possibly the most confusing one at first, is set builder notation. And so set builder notation, if I wanted to, set builder notation works like this. You put a curly brace on both the edges, and you put a straight vertical line in the middle. On the left of the vertical line, you write the variable in question, and in this side, you write the property of the variable you want to specify. The line in the middle is read such that. So for example, suppose I wanted to put x greater than 3 in set builder notation. And really, I know it's confusing. This is the most confusing probably because it's the most straightforward almost. The way you put that in here is you put curly brackets on either end, just like I have here. You put your straight line in the middle, right? The variable we were talking about was x, so I put that over here on the left side. The property of the variable is over here on the right. So really, all you need to do is write the variable, a straight line, and restate the problem. I know, it's ridiculous. I know that look. It's ridiculous, right? Yeah, so when you boil down your inequality and you say blah, 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 I boil it down to x is less than -5, and I ask you to put it in all 3 forms. First, you're going to graph that. Then you're going to put it in set builder notation, which is really just curly brace. X is the variable, so I write x here. Straight line means such that x is less than -5. It really is just restating the problem at this level. They become more complicated later, but right now, you just say, that's my variable, such that, restate the solution. Okay, so that is set builder notation. this kind of notation, this is far more useful in this class, and you're going to be using a lot more in your other algebra classes coming after this. So in interval notation, we just write the two numbers that are the endpoints of the interval we're talking about, and that's it. And we encase them in the appropriate brackets, right? And so for an interval notation, let's look at this example. Suppose I was about to put this into interval notation. I can see that the leftmost side of the interval is 2, the rightmost side is 4, and so I put it in the interval form 2 comma 4. And this is it. This is the interval. Right? Notice I used round brackets at the edge of the interval because these are less than but not equal to signs. If they were equal to, then I'd use square brackets. Okay, so here, why don't I just do that same problem if it were equal to the other version, right? If I wanted to put 2 less than or equal to x less than or equal to 4 into interval notation, I would just say 2 square bracket 4 square bracket. Okay, the square brackets are because of the little line underneath the inequality. Okay, so this is what we call those things. When they're both round brackets, we call that an open interval. When they're both closed, we call it a closed interval. These guys are called half open intervals. That's when one side is closed, one side is open. And integrals with infinity. Sorry, not integrals, intervals. Okay, and so what do I mean by an interval at infinity? You're like, well, what are you talking about? Well, we just drew one out here. It just wasn't so obvious. So with this one, if I wanted to graph that interval, I'd come over here to -3. I would draw a closed dot because it's a square bracket, and that means it's a closed interval. And then I draw an arrow to -infinity. Right, and so that's why I have -infinity as my left endpoint with a round bracket, because we never reach infinity. It's impossible. Okay, for this one here, the interval 2 comma infinity, I'll graph that on the other side of this. Right, I'll graph that in different color ink here. So for that one, we would start out at 2. We notice it's a round bracket, so that means it's either a round bracket here or an open dot. I'll just have an open dot. And it goes, the rightmost point is positive infinity, so that means the arrow points to positive infinity. Okay, so on page 129, there is a great table with all of this stuff in it. It has the comparison between interval, set builder, and graph. If you're not sure how to complete your homework assignment, if I ask you to do all 3 solution types, come to this page and check it out. And by the way, on the exam, I'm going to ask you to give me answers in all 3 solution types, even the goofy one.
What was the exam again?
Tuesday. Yeah, so tomorrow we will have our review, and then Tuesday is going to be the exam. Okay. So here is an example of a problem you might run into. Graph t is greater than or equal to -2 on the number line, and then write the solution using both set builder and interval notation. Okay, so that's 3 different solution types to this same problem. So the first one, they want us to graph this on a number line. To do that, I'm going to draw this extra straight line. You guys can use your imagination as to the straightness. Okay, so now they want me to graph t greater than or equal to -2 on the number line. Right? And so which direction should I draw my arrow? Positive direction, right? Yeah, exactly. Because t is greater than -2. If you're ever confused to that, I know when you're in the exam though, sometimes things that were simple become confusing. If you're ever confused, take a test point, right? Say, well, I don't know. If I drew the arrow in this direction, 0 would be there. Would 0 make this true? Yeah, obviously. So you're on a good path. So yeah, you start at -2. it is greater than or equal to, so you either draw square brackets here or a closed dot, and then you draw your arrow going to infinity. Okay, so now let's put that solution in both set builder and interval notation. So right below this, I'll use interval notation. Right here, I can see my leftmost point is 2. My rightmost point is way over here at infinity. So I'm going to have, what kind of brackets should I have? Square, yes. Boom, square bracket at -2, comma, positive infinity. What kind of brackets should I have here? Round, right? Because you never reach infinity, right? Round. Okay, so that is interval notation. Now let's do this using set builder notation. I know it seems goofy to even put things like this, but you know, they use this in a good way later on, so it's good to get used to this concept. So we say the variable we're talking about is t. We say such that t is greater than or equal to -2. Okay? What's up?
On the outside of the set builder notation, do you always put the one before the straight line, the one that's bigger, that's big?
Oh, okay. Does it matter which order these two come in?
Yeah.
No. Good. That's an excellent question. No, it doesn't. Yeah, it's just the statement that matters, right? Yeah, that's a good question.
-2 outside.
Right, and so this is an equally valid set builder notation if you said -2 over here, as long as you kept your inequality straight, as long as it's still less than or equal to t. Is that your question?
No.
No.
The t that's outside of the straight line, but that's still in the brackets.
This guy here? Yeah.
Is it always the one that's big, like you said, bigger?
Gotcha.
Greater?
That's another good question. So no, so what goes here is the variable, right? It doesn't matter what's getting eaten, what's smaller, what's bigger, it's the variable that goes here. Yeah, and so if we're using z as a variable, z goes there.
Oh.
Yeah, if we're using k as a variable, k goes there.
So it's only used with the letters.
Yes, exactly. Like if we wanted set builder notation for something else, like say, let's say it's k less than 500.
Okay.
Huh?
Okay.
Yeah. Okay, so so then we'd write k such that k is less than 500. Yeah, it's the variable that goes out there. All right. Yeah, good question. Okay. So now we go into how to solve these. What you'll notice is that the addition principle and the multiplication principle for inequalities is almost the exact same, right? You can see down here they go about this the same way that we did when we first learned this concept, right? This just says if you add the same thing to both sides of an inequality, the inequality is maintained. And so when we want to solve an inequality and we need to isolate a variable, we can add or subtract something from both sides to isolate that. Okay, here's a great example. For this first one, they want us to solve this equation, x plus 2 greater than 8, and they want us to put this in set builder notation, interval notation, and graph form. So just like if this were an equal sign in the middle here, I'm going to treat this problem almost the exact same. In this problem, I am going to treat the exact same. I'm going to subtract 2 from both sides because the addition principle is still valid. This is going to give me x greater than 8 minus 2, which is 6. All right, so in that case, we didn't divide or multiply by a negative number, so everything was the exact same as it would have been in an equation. So let's go ahead and graph this. Draw a super straight line. I'd label 6 being my point in question. I notice that all x must be greater than 6. So I draw an open dot and an arrow to positive infinity. For my interval notation, I have an open bracket or a rounded bracket. I put my leftmost endpoint in there, being 6, and then my rightmost endpoint on the other side. Of course, a round bracket at infinity because we never reach infinity. All right, the last point, set builder notation, curly bracket. My curly brackets are getting progressively uglier as the class goes on. I don't know why I'm not able to make those today. Okay, so x such that x is greater than 6. Curly bracket. There we go. That one wasn't as bad.
That was okay.
It was, but it's not.
That one looks like a 3. A messed up 3. Like you tried to use your other hand to write a 3.
Well, it's abstract. You just have to. All right. So.
Get blurry. Hold on.
All right. So suppose we're supposed to solve a slightly bigger one of these, right? Remember, we treat it exactly like we would have treated an equality. So if I have 3x minus 1 less than or equal to 2x minus 5, kind of just like I do with the equations, I'm just going to collect all my variables on the left, all my numbers on the right, see how this works out. So I'm going to go ahead and subtract 2x from both sides, minus 2x, minus 2x. These two x's will go to 0, and then I'll have 3x minus 2x, which gives me a single x. Right, minus 1 less than or equal to a negative 5. Okay, now I'm going to go ahead and add 1 to both sides. Plus 1, plus 1. And that gives me x less than or equal to negative 5 plus 1, which is negative 4. Okay, so I went about that the exact same way that I would have solved an equation. All right, I'm going to go ahead and put the solution in all three forms. So, graph form first. I label 0, then I label negative 4, and then I notice this is x is less than or equal to, which means it's a closed dot, or a square bracket, if that's what you prefer. And then you draw your arrow to infinity, because it was x less than or equal to. Okay, so now let's do our interval notation. So this is slightly different from the ones we've seen before because we point to negative infinity. So now negative infinity, way over here, that's our leftmost endpoint. And our rightmost endpoint is now negative 4. So I have a round bracket, negative infinity, comma, negative 4 with a closed bracket because it's less than or equal to. Okay, now for the weird one. Curly bracket. It's still ugly, I don't know. I just need some clip art that I can maybe paste up there every time. Okay, so curly bracket, x, such that x is less than or equal to negative 4. I just restate what I just found and then close it out. Okay. Alrighty, the next one. So we just went over the addition principle. This is the only rule that things might get a little bit weird on. The only one. So the addition or the multiplication principle says when c is a positive number, you can multiply both sides of an inequality by c and it will maintain the inequality. However, this is the big caveat. When c is a negative number, you'll see
I see what you did there.
So when c is a negative number, you'll notice that the inequality sign actually switches when you multiply it through, right? It just flips the other direction. That's what happens when you multiply or divide by a negative number. Okay, so for example, if I had some rando inequality, let's say 3 less than 5, if I multiplied both sides of this by a negative 2, negative 2, negative 2, I would have to flip this inequality. So I flip it the other direction. Negative 2 times 3 is negative 6. Negative 2 times 5 is negative 10. And we can see this is still a true statement. Negative 10 is less than negative 6. All right? So let's do some better examples with this. Okay, so for this first one, this is not one of the weird cases of the multiplication principle. This is one of the easy cases. The coefficient's positive, which means we're going to multiply through by a positive number. So what's the reciprocal of 1/4? 4. So I multiply both sides by 4. All right, the 1/4 and the 4 cancel on this side, and this leaves me with x less than 7 times 4, which is 28. So right here, I am only asked to graph the inequality, so I don't need to do the other two solution types. Pay attention, though. When you're asked to do the other solution types, you'll get docked points if you don't do them. Okay, so I'm asked to graph this. I label 0. As always, I'm going to label the point in question, 28. X is less than but not equal to 28, so I'm going to leave an open dot here, and I'm going to draw my arrow to negative infinity. And I know my graphs are super ugly because I'm just like, I just draw all over them. It's okay to make your graphs ugly like that too if you want to. You can also make them very pretty and nice if you want to. You don't have to make your graphs like mine. These are right on the edge of unacceptable. Okay, here's one of the cases that we really want to pay attention to, okay? Super important here. I notice that all I need to do is get rid of the coefficient on the y to have it solved. The coefficient is a negative number, though. So when I notice that I'm dividing by a negative number, I'm going to draw a little arrow down here so I remember to switch the direction on this, right? So once it was facing right, now it's facing left, and now I cancel those negative 2's that were attached to my y, and now I have y is greater than or equal to 18 over negative 2, which is equal to negative 9. All right, so when you divide or multiply by a negative, swap that sign and then just go with it. So let's graph this guy. I have a 0. I have a negative 9. Right here it says y, we're looking for all y that are greater than or equal to a negative 9, which means I have my closed dot, or square brackets if you prefer. And then I have, maybe I'll try to draw it real pretty this time. It's not working. Then I have my super nice line. Okay, this is a class about imagination. Okay, so any questions on that? Dividing by negatives, multiplying by negatives? Okay, yeah, just remember, if you're at a loss, solving inequalities is the same as solving equations, except for when you multiply or divide by a negative number. That's really the only big difference. Okay, so let's go through a couple examples of doing both of these concepts together. So for this first one, I notice I have a negative 5y. I need to isolate that. So I'm going to go ahead and subtract 6 from both sides so I can get rid of the constant that's next to it. So minus 6 minus 6. These two 6's go to 0, and I have negative 5y is greater than 7 minus 6, which is just 1. Okay, so now I need to divide both sides by the coefficient, which is a negative 5. I'm going to draw a little arrow down to tell me I need to switch that. Bing, bing. And then I have y is less than a negative 1/5. All right, since this problem did not tell me to graph, just said solve, I can leave my solution just like that. All right, here's one with some decimal places. Take out the old handy dandy calculator for this one. Okay, so for this one, once again, I want to isolate this negative 7.2p, so I'm going to get rid of this 16.3. I'm going to do that by subtracting it from both sides, so minus 16.3 minus 16.3. These guys go to 0, and I have negative 7.2p is less than or equal to whatever this is, 8.18. I have 24.48 here, negative. Okay, so now I have a negative coefficient, so I just have to remember that I'm going to need to switch this sign. Divide by negative 7.2, divide by negative 7.2. And this is, when I draw this arrow down, I just do that to remind myself. I'm a very forgetful person. And even when it's the main point of the problem, sometimes I forget to switch this. So I draw the arrow down to remind me that something needs to be done here. So I swap it. These guys will cancel, and then I just need to punch this into my handy-dandy calculator to figure out what's going on.
Oh, I have a graph on my...
Yeah? On what, your calculator?
Yeah.
Hit clear. 3.4 is the answer to this. Once again, the instructions didn't say I needed to graph it or put it in set builder or interval, so I'm just going to leave it as is. Ah, this one's pretty. Okay. Just like we would with a normal equation, we start by simplifying everything, collecting the like terms, and then going about our business isolating our x. Okay, so for this one, I'm going to go ahead and do my distribution first, and that's going to allow me to simplify everything. So I have 1 minus 3x plus 3 times 9 is 27. Whoops, I better be clear here because my 7 looks too much like my less than sign. So 27 with these little things. Less than 5 times x gives me 5x. 5 times 6 gives me plus 30. Then I have minus 2. So now I go through and I collect any like terms that I can. It looks like I still have a negative 3x on my left side, and I'm adding 1 and 27, which gives me 28. On my right side, I have 5x and then 30 minus 2. That gives me a positive 28. Okay, I'm going to start tossing all my variables over to the left side. So I'm going to go ahead and subtract 5x from both sides. Minus 5x, minus 5x. These 5x's will cancel, and then I'm going to have negative 8x over here, plus 28, less than 28. Interesting. Okay, so notice what happens next here. When we have the same number on both sides of the equation, we just subtract it from both. Minus 28, and those go away. And we have negative 8x is less than 0. You might be tempted to quit now, but remember, we have a negative 8 out there. So we're going to need to divide both sides by a negative. And even though this seems almost too simple, you still have to switch this. Otherwise, it won't be correct. Right, so these guys cancel into 1, and we have x is greater than 0 now. That would be your solution. Okay. Any questions about solving inequalities? Okay. Let's go to solving inequalities and applications. So, this page, what page is this? I don't know. This is some page in your book. This is a page in chapter 2.7. This is a pretty helpful page. You can see it sort of goes over those English to math transitions like we did in the earlier chapters, except for these ones have to do with inequalities, which can get a little twisted up, right? Like, what does it mean when you say no less than, right? If you say x is no less than y, right? Is that which one's greater? Right? Sometimes that can be confusing. This will help you work that out. Right? And if you say x is no less than y, what you're saying is x is greater than or equal to y, right? Because it could be equal, just not less. All right, so I would definitely recommend going through that section as part of your homework and just read through all of them, right? And just to get your head used to it. Okay. There we go. Here are two of the more commonly used ones. Somebody says the quantity x is at least some amount q. That means x is greater than or equal to q. When somebody says the quantity x is at most some amount q, that means x is less than or equal to q. Okay, so let's go into the first example problem. So this is like a total value problem that's just put in inequality form, right? And so this is there's a setup fee, right? So there's a base fee, and then there's a per hour or per person fee. So to cater a party, Papa Roo, great name, charges a $50 setup fee plus $15 per person. The cost of the hotel, the cost of Hotel Pharmacy's end of season softball party cannot exceed $450. How many people can attend the party? Okay. So, cannot exceed. So let's write out what that means. Cost of party cannot exceed $450. What do I put here? What kind of sign do I put in the middle of these two? What goes right here? Greater than, equal than?
Less than or equal to.
Yeah, less than or equal to, because it can't exceed. It could equal exactly 450. It just can't be over that amount. So we put less than or equal to in there. So now all we need to do is figure out what the cost of the party is. All right, we have a $15 per person charge. So let's just define that variable. So we're going to say let X be the number of people. Okay, so the total cost of the party is the $50 setup fee plus $15 per person. That is 15 times X for X number of people. And we say that has to be less than or equal to $450. Okay, so now we are set up. All we need to do is solve this guy, call it a day. All right, so the 50 is a constant term out here, so I'm going to subtract it so I can isolate my X. So I have minus 50, minus 50. Okay, those guys go away, and I have 15X less than or equal to 450 minus 50, which is 400. Okay, now I'm going to divide by the coefficient. The coefficient is not negative, so I don't have anything extra to do here. I just cancel my 15s and I say, thank you very much. X is less than or equal to 400 over 15, which is something ugly. Oh, yes, we want the ugly number because we're talking about we're talking about number of people, so I'm going to put the decimal out here so that we know we don't have to calculate through the fraction, right? So we're saying X must be less, and you're right on the right track. X must be less than 26.6 people. We don't have a sixth of a person, right? And so obviously, yeah, he's got to have 26 people or less, right? And that's what you'd put in your sentence. You'd say, Papa Roo, or no, you'd say the Hotel Pharmacy's, I just like saying that name, the Hotel Pharmacy's end of season softball party cannot have more than 26 people attending, right? And so the people they don't like, they're going to have to tell them they can't come. Okay, so that's a total value problem. Now we're going to go into the average or mean problems. One of these will definitely be on the exam. So let's just remind ourselves what it means to be the average or the mean, and then remind ourselves of how we calculate that number. So remember that the average or the mean is, well, we won't explain what it is. You guys kind of know what the average is. How to calculate the average of a set of numbers is you add up all those numbers and you divide by the number of numbers. Okay? So for this set, if I wanted the average of this set, it has 4 numbers. I would add all those numbers and divide by 4. Right? So this particular average is 2 plus 2 plus 4 plus 8. That is 16 over 4, which is equal to 4. Right? So the average of all these numbers is 4. Okay, if we do this with a set of 5 numbers, it's the same thing, we just divide by 5. But pay attention to something real important here. 0 was one of the numbers that I averaged. I made sure to count that into the total count, right? Just because you have 0 doesn't mean it goes away, right? 0 still counts. You know, you don't add it into the total numerator, but the total number of numbers is affected. So 0 is included. Alrighty, let's do a financial aid problem. So, full-time students in a healthcare education program can receive financial aid and employee benefits from Covenant Health System by working at Covenant while attending school and also agreeing to work there after graduation. Students who work an average of at least 16 hours per week receive extra pay and part-time employee benefits for the first 3 weeks of September. Dina worked 20 hours, 12 hours, and 14 hours. How many hours must she work during the 4th week in order to average at least 16 hours per week for the month? Okay, so let's just go ahead and write down sort of what we're going to make out of this, right? And so what we are figuring out, we're saying average hours, right? So they're saying they must average at least 16 hours per week, right? And so we have average hours, we have the number 16. What do we put in the middle here? Greater than, less than, what? Yeah, greater than or equal to, with the greater than part being directed at the average hours, right? Because she needs those hours to be greater than 16 to get any benefit. All right, so now we're going to draw out our formula for the average hours. So we're just going to pay attention to what she did on the first 3 days. So I have 20 hours plus 12 hours plus 14 hours. And here's the trick to the whole problem. We don't know what she works on the last day, so we have plus x. That's the trick, right? Now, draw out our fraction, and we put how many numbers we have up there. And there are 4. You include x in that count. Greater than or equal to 16. All right, so the next step, don't get ahead of yourself on this. A lot of times people want to start canceling stuff right away. Just calm down, add up your numbers, and take it step by step. So we add up these guys first. That gives us what? 32, 46? Good. 46 plus x over 4 greater than or equal to 16. All right, now you still might be tempted to start trying to cancel stuff because you've got this plus sign on the top here. Don't do that. Just get rid of that fraction first. Multiply both sides by something that's going to cancel this denominator. Boom, boom. Then we just have a regular problem on our hands. 46 plus x is greater than or equal to whatever 16 times 4 is. 49? I don't know. 64, 9 plus, okay. 64. All right, so now I have a regular inequality. I'm going to go ahead and isolate my x by subtracting 46 from both sides.
What did we do? Sorry.
Well, like in between these two steps? Where you lost? So, okay, hold on. Let me just back it up because this is the step that gets a little weird. So when you reach this point, why am I not erasing here? There we go. So when you reach this point, sometimes it's tempting to try and split up this fraction, right? But you don't really want to do that. You want to clear this fraction because this is inconvenient for us, right? So just like we would multiply both sides by 4 if we had 1/4 x, we can multiply both sides by 4 to get rid of this 4 in the denominator, right? And so what this should be, or what this can be written as, is 1/4, right, times 46 plus x. This is saying the same thing as this is, right? And so I see that 1/4 coefficient, and I say, I don't want to deal with that. That's a fraction. I'm going to multiply both sides by its reciprocal, so I don't have to deal with it anymore. So I have 4 times 1/4, and then 16 times 4. These guys will cancel to 1,
Okay,
and that'll get rid of 1.
the right side as well. Okay.
Yeah, we multiplied both sides, yeah. And that's just, it's a method of simplification, really. Okay, so now I have 46 plus x greater than or equal to 64. So I'm going to subtract 46 from both sides. Minus 46, minus 46. and I have x is greater than or equal to 64 minus 46. Yes, thank you for that. X greater than or equal to 18. So, come back up to the original problem, and we can say that this lady, what's her name? Dina needs to work at least 18 hours during her last week to get the benefits she wants. Okay, so I'm going to just do a few extra problems here. Yeah, sure. This one? Yeah, sorry. Yeah, by the way, if I ever am going too fast up here, remember, I have everything written down ahead of time, so it's really easy for me to just skip to the next page, but you guys are taking notes. So I don't get offended one bit or mind one bit if you guys say, hey, calm down, Speed Racer. Okay. Even if you want to just stop and think about the problem for a couple seconds, that's okay. All right. Good? Okay. Alrighty. So here is, here's another total value problem. All right. So for this one, how about I let you guys set this up for a few minutes, and then we'll just launch into the problem. So why don't you guys go ahead and try and figure out what the setup for this one is. Right? And I'll just give you a minute to do that, and then you can check your work when I start the problem. Right? So this is total value problem. Okay, so let's go over how we set this one up. So right here, we can kind of pick out the key sentence. Gary, there's supposed to be an S on that. Gary remembers being billed over $150. So this is basically what we're trying to explain here. Gary's, whoops, that's a weird B, bill, right? Being billed over $150 was over, greater than 150. Now we just need to figure out what Gary's bill was. Well, the plumbing charges $55 for each time they show up, plus $40 an hour. So first of all, we got to define our variable. I always forget that. So we're going to say let hours equal X. Okay, so Gary's bill was $50 base pay plus $40 times X hours. And they said that was over 150. How'd you guys do on your setup? So-so? A few things to work out? Good? Yeah. Yeah, a lot of times, especially with these ones, the setup's the most important part. So we know what to do from here.
Again.
Yeah, again, right? Okay, so we want to isolate this 40x. So I'm going to subtract the constant from both sides, minus 50 on both sides here.
55.
55?
55 plus.
Oh, hey, thank you for that. Jeez. I am,
Costing me money.
right? Time is money. Okay, 55, nice. So I have minus 55, minus 55, good. Okay, so these guys go to 0, and I have 40x greater than 150 minus 55, which is, I believe, 95. Okay, divide both sides by 40. It's a positive number, so I don't have to switch any inequality sign. So I have x is still greater than 95 over 40.
75.
All right, 2.375. All right, so Gary was billed over 150. How long was RJ's there? Well, it says that X is greater than 2.35. So we can say RJ's was there for more than 2.375 hours. All right. Here's another one. You guys take a couple of minutes and try and set this guy up. See if you can figure out how to set this one up. Okay. So you'll notice here, right here, it says, Vanessa's financial aid says her tuition cannot exceed $2,500. Okay? So we're just going to write that sentence out. And so what we want to say is tuition cannot exceed $2,500. It could be equal to, though. So it could be greater than, wait, it cannot exceed. Whoa, calm down. So it must be less than or equal to 2,500. Yeah. All right. So now all we need to do is come up with our formula for tuition. All right. So right here, we have a $95 registration fee plus a $675 per course fee. So once again, I'm going to go ahead and define my variable late in the equation. So let the number of COU courses equal X. Okay, so $95 registration fee plus however many classes she took times the tuition cost, $675 times X. That's got to be less than or equal to 2,500. You guys know what happens here, right? We subtract the 95 from both sides, and we end up with 675. X is less than or equal to 2,500 minus 95, which is 2,405. Okay, go ahead and divide both sides by 675. Wow, that's an ugly one. Okay, so X is less than or equal to 3.5629. And then some more stuff. Okay, so let's take a look at the original problem. Oh, okay, of course, she's dealing with whole numbers. So X has got to be less than or equal to 3.5. You can't register for half a class, so she's got to have less than or equal to 3 classes that she registers for. Okay. Here's one. Here's one that's related to a strange problem on your homework. I can't remember if I deleted it from the homework list or not, but the problem has to do with a box size of something being mailed, so this is a little bit different than what we've done so far. This has to do with area. So, Rhetoric Advertising is a direct mail company. It determines that for a particular campaign, it can use any envelope with a fixed width of 3.5 inches and an area of at least 17.5 inches. Determine, in terms of an inequality, those lengths that will satisfy these constraints, right? So this is a little bit different. We're talking about an area formula now. So let's write out basically what they're trying to say. So they are saying the area, what does it say? It says at least. The area has to be at least 17.5 square inches. So we're saying area must be greater than or equal to 17.5 square inches. So now we just need to figure out our formula for the area. To do that, just draw a quick diagram of this envelope. Not that you actually need this. So We have curly brackets. That's super ugly again. I'm just going to write 3.5 over here.
Is that
3.5.
Okay,
Yeah, that's an. Well, you got a problem with my envelope? What? It's an awesome envelope. Okay, so we have 3.5 inches there, and we're going to say this side is just X. All right, we're not sure what that's going to be.
I looked up and I thought you opened Gmail. What?
So now we just got to remember, for any square thing, right, the area is just width times length, right? Width, 3.5, length, X. 3.5x greater than or equal to 17.5. Divide both sides by 3.5. And that gives us X has got to be greater than or equal to whatever this is. 5? What? 5? Cool. X has got to be greater than or equal to 5. Right? Since we were talking about inches, we're going to say that the length of one of these envelopes must be at least 5 inches. Any questions about that one? I believe on your homework, you're going to be dealing with something very similar to this, but it's going to be with a three-dimensional box. So you're going to need to think about the volume formula rather than just the square, the area formula. Okay? Volume being width times length times depth or whatever else dimension you want to put in there. Okay. Moving on. Okay. We'll do one more average problem. Then you guys can run away. So, and remember, average problems are going to be on the exam. All right, so there's this dude named Bill, and he has to earn a 70% average from, he has to earn at least a 70% average exam score in his math class to pass. There are a total of 5 exams. On the first 4 exams, Bill scored these numbers. What would Bill need to score on the final exam to get at least a 70% average? So, we're saying Bill's average must be at least a 70%. So we're going to say greater than or equal to 70. All right, so Bill's average, we can calculate that by adding all these up, including an x, and then dividing by the number of numbers. So I have 60 plus 78 plus 88 plus 49. And then the final test he's going to take plus x, because we don't know that yet. Okay, nice. Right? So what number do I put on the bottom here?
5.
Nice, 5, because there's 4 numbers and there's 1 unknown. So that gives us 5 total. Greater than or equal to 70. What did you say it was? 275 plus x. Okay, when we sum all those numbers up. Now, remember, a lot of times you guys might be tempted to start splitting fractions up and doing things that are really confusing. Don't do that. Just multiply through by a number that will cancel this denominator. That number is the denominator itself, 5. Okay, so once I multiply through by the 5, these cancel, and I have 275 plus x is greater than or equal to 70 times 5, which is 350. All right, I'm going to subtract the 275 from both sides so I can isolate my variable. These guys go to 0, and I have x is greater than or equal to 350 minus 275, which I think is 75. All right, so Bill needs to get at least a 75% on this last exam in order to get his goal in the class and pass. All right, so just one quick little mention about this problem. Notice that I didn't convert any of my percentages into decimal form. You can do that if you want to, but your answer will also be in decimal form. So if you do it to one of these percentages, do it to them all, and remember your answer is in that form. But you don't have to do it to any of them. I prefer just to leave them. So that's it. Thank you guys for your patience today, and study hard.